This video will cover independent component analysis, or ICA. ICA allows us to describe data as a linear combination of statistically independent components. There is no dimensionality reduction being done here. The typical problem used to demonstrate ICA is the cocktail party problem. Two people are conversing at a party. Two microphones are positioned at different parts of the room. The microphones give us audio signals, which we will refer to as X, our observed signal. The spoken signals, the actual original signals that are not observed, are S1 and S2. The microphones pick up different combinations of the voices, and so they are represented as linear combinations of the actual signals. Both A and S are not observed. Here, we have a graphical representation of this concept. These are two speaker signals. These are two observed signals, that is, what is picked up by the microphones. The goal is to recover the original signals, given only the observed data. The setup is like this. We have x of t equals a times s of t, where x is an observed signal over time, or you can think of it as just a vector. S is the original signal over time, and A is an unknown square invertible matrix called a mixing matrix. X of t and S of t are n-dimensional vectors, where n is the number of speakers and microphones. The observed signals are a linear combination of original speaker signals. ICA seeks to find A and S. If we find A, we can solve for S by taking the inverse of A. We will call the inverse of A W, so we can refer to the rows of W as W sub I transpose. How do we solve ICA? We have to determine the log likelihood of the training data that depends on W, and we need to perform iterative updates to improve the estimated W. Let's start with the log likelihood. We're trying to find W so we can recover the original signals, so we need the log likelihood of W. This is given by the following equation. I will go through this a little bit, but if you want more details, please look at the readings posted on WebCampus. This portion is the determinant, so this is just a constant. This is the derivative of the sigmoid function. This log likelihood equation comes from taking the logs of the probability density function of x of t at each time step. If p is the density function of x of t, then we get the following equation, where p sub I is the density of the individual source I. The log of the product is the sum of the logs, so that's how we go from the equation down here to the one above. Then we just sum over all the time steps. But where does the sigmoid come from? We don't know the density of the individual sources, so we have to approximate them with something that works well, the derivative of the sigmoid function. Remember, the sigmoid function looks like this. The sigmoid function satisfies the properties of a cumulative distribution function, and by differentiating such a function, we get a probability density function. So basically, it works in practice and has the right properties, so we use it. How do we update our W? Using stochastic gradient descent, and our update equation is this. That's it. We basically just use gradient descent to update the inverse of our mixing matrix W, and then we use that to recover the original signals. So now we understand how each observed signal was generated as a linear combination of actual original signals. ICA is not reducing dimensionality, but rather describing the data as linear combinations of source signals.